Hey everyone, and welcome to The Explainer. We're kicking off a brand new series today, diving deep into the book Patterns of Distributed Systems. And we're going to start with the most fundamental question of all. Why do we even need these things in the first place? Let's get into it.
This quote from the book's preface really just hits the nail on the head. To get a real handle on distributed systems, we have to get rid of any ambiguity. This isn't just about choosing a cool technology. It's an evolution, and it's driven by some very real, very physical limits.
All right, so every story has a beginning. And for a growing application, the origin story almost always starts right here, with a single, solitary server doing all the work. Now, any server, it doesn't matter how powerful or beefy it is, it really only has four fundamental physical resources to work with. Its CPU, its memory, its network connection, and its disk. That's it. So what happens when your application gets really popular? Well, those resources get pushed to their absolute breaking point. And this right here, this is the classic bottleneck. It's kind of the paradox of success, isn't it? The more people love your app, the slower and more painful it becomes to use. Requests start piling up, wait times shoot up, and that amazing user experience you built, it just evaporates. The system that was once lightning fast is now just frustrating. So clearly, that can't last. The system has to evolve. It's time to take the first steps beyond that single overloaded server. The first, most common move is to separate your concerns. You take the stateless application logic, that's the part that doesn't need to remember anything from one request to the next, and you put it on one server. Then you take the stateful database, the part that has to remember everything, and put it on another. Makes sense, right? Well, sort of. But all you've really done is move the problem. Now the database itself becomes the new bottleneck. And since you can't just keep buying a bigger and bigger server forever, that gets ridiculously expensive really fast, the next logical step is to divide the data itself. You spread it out across multiple machines. That way, you can process requests in parallel and handle way more traffic. But this solution, well, it creates a whole new kind of crisis. Because the more machines you add to the mix, the more individual points of failure you have. And at a certain scale, failure stops being a possibility and becomes, well, inevitable. This right here requires a total shift in your mindset. You see, in a system with one server, failure is a possibility, something you worry about. But in a system with thousands of servers, failure is a certainty. The question is no longer if something will fail, but when it's going to fail. Just look at this data. It's from a famous talk by Google's Jeff Dean, and it makes the abstract idea of failure shockingly real. We're talking about 1,000 machines just disappearing because a power unit fails. Entire racks of servers can just go offline in an instant. For a large-scale system, this isn't some rare disaster. It's just another Tuesday. Okay, so if failure is just a fact of life, how in the world do you build a system that can actually survive it? The solution, and this is a huge concept, is replication. Replication is basically the hero of our story. It's the key technique that masks all this chaos from the end user. By keeping copies of your data on multiple machines, if one server crashes and burns, another one is right there, ready to take its place. To the user, it just looks like nothing ever went wrong. But, and this is a huge but, replication is not a magic wand. It introduces a whole new class of really complex challenges. I mean, what happens if a server crashes right in the middle of an update? Or a network message gets delayed? What if the clocks on two different servers disagree on what time it is? The software itself has to be smart enough to handle all of this. So this entire journey, from that one lonely server to splitting things apart to dealing with constant failure, it all brings us right to the core definition of a distributed system. This is the why. A distributed system isn't just a bunch of networked computers. It's an architecture that's specifically designed to solve two core problems: scale and failure. Everything else we're going to talk about in this series really flows from that. And that brings us to the whole point of this book. The problems of dealing with scale and failure, they've been solved before, many times. These solutions are called patterns, and you can really think of them like Lego blocks. They're proven, reusable components that you can use to build robust systems without having to reinvent the wheel every single time. So as we wrap up, I'll leave you with this question. Think about the systems you use every single day. They are almost certainly distributed, but do you know which patterns they're built on? Join us next time as we start breaking down the very first of these essential patterns. It's going to be great.